Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we are going to use the standard cell potential to predict the spontaneity of a chemical reaction in the forward or reverse direction. And so overall, this concept can be summarized in a couple of sentences. And so when the calculated standard cell potential is positive, in other words, it's greater than 0, then the forward reaction is going to be spontaneous. And so when the standard cell potential is negative, then the chemical reaction in the forward direction is going to be non-spontaneous. And so typically, if you get a reaction, a forward reaction that's non-spontaneous, in other words, you have a negative standard cell potential that you calculated, then that basically means that if you were to reverse or flip the equation, you would have to flip the sign of your standard cell potential, and so it'll go from negative to positive. So long story short, if the forward reaction is non-spontaneous, then the reverse reaction is going to be spontaneous. So looking at this example here, we have zinc solid reacting with copper 2 ion to produce zinc 2 ion and copper solid. And so if we wanted to determine if the forward reaction is spontaneous, then we would need to calculate the standard cell potential. And the standard cell potential was already calculated in the previous lecture video for this reaction. And so it turns out that the standard cell potential is going to be 1.150 volts. And so since this answer is going to be positive, then that tells us that the forward reaction is going to be spontaneous. And so that implies that if you were to reverse this equation such that you have copper solid reacting with copper or with zinc 2 ion to produce zinc solid and copper 2 ion, the reverse is going to be non-spontaneous. And you guys will get a standard cell potential that's negative 1.10 volts. So the number stays the same, but the signs flip when you flip the equation. And so what that tells us is that if we wanted to use this chemical system to do some type of work, so this spontaneous reaction is going to fuel a non-spontaneous reaction, if you will, then we will have to manipulate the setup of this chemical reaction such that they are not in the same solution. And so we're going to take this solid zinc, which is going to be our electrode, and we're going to immerse that in a solution of zinc ion. And we're going to take this copper, this solid copper, and this is going to act as the electrode for the cathode half of the galvanic cell. So when we connect the zinc anode to that of the copper cathode, this will tell us that the transfer of the electrons from anode to cathode will be spontaneous because its calculated standard cell potential is greater than 0. And therefore it would make sense for the electron to flow from left to right in this case. And so what we're going to do is we are going to go through a few examples that will demonstrate this concept. that'll allow us to determine whether or not our current chemical equation, such as this, is going to be spontaneous or non-spontaneous in the forward direction. So let's go ahead and start. So to determine if this chemical reaction is spontaneous, we need to calculate the standard cell potential. And one way to calculate the standard cell potential is to simply take the difference between the potential, the reduction potential, and subtract that from the potential that describes oxidation. And so what I did is, instead of having us to look through the reference sheet of the standard reduction potentials, I went ahead and just copied and pasted the values that's necessary for this problem. And so we only have two numbers to work with to figure out the standard cell potential. We only have negative 1.66 volts and positive 1.5 volts. And so we need to figure out whether or not this 1.50 volts goes in the front or goes in the back. And the same thing can be said for this negative 1.66 volts. Is that value going to go in the front, or is it going to go to the back? And the only way that we can deduce that is to figure out which half reaction is undergoing oxidation and which half reaction is undergoing reduction. And the only way for us to determine what's being oxidized and reduced is by comparing the oxidation numbers. And so really the oxidation numbers only has one purpose in its chemistry life, and that is to help you determine what's oxidized and what's reduced. Once it's fulfilled its purpose in its life, it can pass away, it can pass on and go to chemistry heaven, and it'll be super content. All right, so we need to figure out the oxidation number for gold. So since this is solid in state, and there's nothing else attached to it, then we can go ahead and say that its oxidation number is 0. It's a pure metal. Here the oxidation number for aluminum is going to be +3. It takes that of its charge. Gold is going to be +3. It takes that of its charge. And aluminum is going to be 0 as well. So now that we've listed our oxidation numbers, what we're going to do is just compare the oxidation numbers for the same element before and after the reaction. And so looking at aluminum, here we have +3, and here we have 0. And so notice that my oxidation number is decreasing as I go from the reactants to products. And so therefore, aluminum is probably undergoing reduction. Now, if I look at my oxidation number for gold before the reaction and gold after the reaction, notice that the oxidation number is going up. And so therefore, that's probably, so it's most likely that the gold is undergoing oxidation with the way that it's currently set up. So now that I know what's oxidized and what's reduced, I can go ahead and place these values in its proper place in this equation. And so notice that aluminum is undergoing reduction. And so since this is the value for aluminum, then I'm going to place negative 1.66 volts in the very front. So the calculated cell potential is equal to negative 1.66 volts. And so since gold is undergoing oxidation, then therefore that 1.50 is going to go at the very back. And this negative sign will flip this sign so that the cell potential does represent oxidation, even though as written, it's a reduction. Right? So this is a reduction potential. And so this negative sign will flip this number so that it represents oxidation. So we're simply going to go ahead and put in plus 1.50. All right, so aluminum, negative 1.66, because it's undergoing reduction. Gold is undergoing oxidation, so this 1.50 is going to be plugged in at the very back. And so if we take the difference between these two, so we have negative 1.66 minus 1.5, that's going to give us negative 3.16 volts. And so the overall standard cell potential is going to be negative 3.16 volts. And so since this value is negative, then therefore the forward reaction is non-spontaneous. And so what this implies is that the reverse reaction, so if we put the arrow this way, if we have solid aluminum reacting with this gold ion, then the reverse reaction will be spontaneous. Here the standard cell potential for the non-spontaneous forward reaction is going to be negative 3.16 volts, while the standard cell potential for the reverse reaction is going to be positive 3.16 volts. All right. So let's go ahead and take a look at another example. And we've been working with a lot of simple chemical reactions, very simple oxidation reduction reactions. And at some point in time, you guys need to be able to determine what was oxidized and what's been reduced for more complex chemical reactions. And so let's go ahead and take a look at this one, just in greater detail. All right, so I'm actually going to rewrite this at the very top, just because I didn't put in enough space. So this one's just a little bit involved. So we have 2 H2O2, and then plus S solid to produce SO2, 2S, just SO2. Okay. And so let's just say that this is liquid in state. All right, and so what we're going to do is we're going to assign oxidation numbers. And when we're assigning oxidation numbers, do not pay attention to the coefficient. And so if you guys go through Tyler DeWitt's video on how to identify oxidation numbers for more complex chemical equations, you guys will be able to see the rules that he listed there. So I'm just going to talk about it very quickly. So the oxidation number for hydrogen, if it's in the position of the cation, is +1. And so the oxidation number for oxygen, if it's a peroxide, is going to be -1, not -2. And so for sulfur, since this is solid in state and since it's by itself, its oxidation number is 0. So for SO2, the only element that we know of in terms of its oxidation number is going to be oxygen. And so the oxidation number for oxygen is -2. For this sulfur, we actually do not know. So notice that we know the oxidation number for sulfur, it's 0 here because it's by itself and it's solid in state. However, when you guys look through the rules for oxidation numbers, there's no direct rule that determines the oxidation number for sulfur. So this is something that we need to find. So before we do that, let's move on to H2O. And so here we have hydrogen, and each hydrogen has an oxidation number of +1. And so what we're going to do is just summarize it as +1. So we're not going to pay attention to the amount. So oxygen, if it's not in a peroxide, it's going to be -2. And so it looks like we know the oxidation number for every single one of these elements. The only thing that we need to determine now is the oxidation number for sulfur and sulfur dioxide. So to do this, I'm going to set this up as a algebraic equation such that the sum of these two will equal to 0 because the overall charge for sulfur dioxide is 0. So since we have one sulfur, I'm going to put 1x. And then I'm going to add that to the oxidation number for each oxygen. Since I have 2 oxygens, I'm going to put 2. And then I'm going to multiply that by the oxidation number, which is going to be -2. And that's going to equal to 0. And so if I solve for x, that's going to give me +4. And so therefore, the oxidation number for this sulfur is +4. And so now that I'm going to erase that and I'm going to just move this here since I've solved for x. Now that I know my oxidation numbers for every single element, I'm going to go ahead and compare those elements before and after the reaction. And so if you look at hydrogen, it's +1 and +1. Its oxidation number did not change. And so therefore, I don't consider it as either oxidized or reduced. So the next thing I'm going to look at is this oxygen. And if you look, you guys have 2 oxygens. Here in this case, you have oxygen here and oxygen here. Okay. And so we see a change in numbers. We're going from -1 to -2 and -2. And so we need to determine we need to look at sulfur before we can determine which side this hydrogen peroxide is going to go where. And so if you look at sulfur, sulfur is 0 to +4, and we only see one place for sulfur. So it looks like these two are going to be connected, leaving me with these two that are going to be connected. Okay. And so because sulfur is only found in one place, then this compound, sulfur dioxide, is going to be compared to solid sulfur. And so that kind of whittles down, if you will, or narrows your choices as to which compound this hydrogen peroxide, the oxygen hydrogen peroxide, is going to be compared to. All right, so now that we have compared these oxidation numbers, we're going to see what was oxidized and what was reduced. And so if you look, -1 goes down to -2. So my number is decreasing. So therefore, the conversion of hydrogen peroxide into water involves a reduction. And if you look at my oxidation number between sulfur in the reactant side and sulfur in the product side, I'm increasing my oxidation number. So therefore, this is going to be, sulfur is going to undergo oxidation. All right. So now that you know what was oxidized and what was reduced, I'm just going to go ahead and use these standard reduction potentials to calculate my E cell. Oops. And so my standard reduction potential for, let me see here, hydrogen peroxide, it's going to go ahead and go in the front of this equation, just because hydrogen peroxide is going to undergo reduction according to my oxidation numbers. And so that 1.77 volts is going to go in the front. And the standard reduction potential for sulfur dioxide, or for sulfur turning into sulfur dioxide, needs to be flipped. And what will flip that is the negative sign that's present in the equation. However, what we're going to do is we're going to place this 0.45 volts in the very back of the equation. So here we have 0.45 volts. And so if we subtract those two values, 1.77 minus 0.45, that's going to give us a value that's positive 1.32 volts. And so now that I know my calculated standard cell potential, by looking at the sign, I can see that the forward reaction is indeed spontaneous. And so that means the conversion of hydrogen peroxide, there's a reaction of hydrogen peroxide and this solid sulfur will be spontaneous in the forward direction. And so I can go ahead and use this chemical equation and create some type of half cell reaction, or I can go ahead and use this chemical equation and create a galvanic or voltaic cell out of it, knowing that the forward reaction will be spontaneous. Therefore, the electrons will spontaneously flow from anode to cathode. Okay. And so, let me see here. Very quickly, I want to talk about the cell notation again. And so here, remember that the cell notation describes the transfer of electrons from anode to cathode. And typically, what's first written is the solid version of that chemical species. In other words, that's going to be the electrode. So anode is oxidation, so you're losing electrons. And so according to my work, gold is going to lose electrons, and it becomes gold with a 3 plus charge. So I'm simply going to put in gold. Oops, that's silver. So that's going to be my electrode. And it's going to produce gold 3 ion. And then once again, this double vertical line represents your salt bridge, which is a separation of the half cell, right? And so my cathode is going to represent reduction, which is going to be a gain of electrons. And so here in this case, your aluminum ion is seen first, and then it becomes aluminum solid. So we're just going to go ahead and write that in our cell notation. So I have aluminum ion producing aluminum solid. And so this is going to be the electrode. So what's going to happen is that if you have these, two half cells, and as this reaction occurs over time, since your gold electrode is going to lose electrons, the gold atoms will be transformed into its ionic form. And so therefore, at some moment in time, you guys are actually going to see your gold kind of shrivel and shrink as the forward reaction continues. And so since cathode represents a gain of electrons, those ions that's in the solution, they're going to absorb those electrons, and it's going to become a solid. So in other words, it's going to stick on to the aluminum electrode that's already there. Oops. And so therefore, over time, you guys are going to see that there's going to be a gain of substance, gain of aluminum. Over time as the reaction proceeds. And so I kind of digress with the pictures over there. Apologize. And so looking at this specific reaction, notice that there's only one element that's solid in state. Notice that in the product side, there's no solid present. So technically there's no metallic electrode, which is actually required for your forward reaction to occur if you were to set up a galvanic or voltaic cell. And so in scenarios like this, a substitute metal would have to take its place. An example of a substitute metal would be like platinum or palladium or something like that. And so for these more complex chemical reactions in which, there's not a defined, like there's no two solid, there's no two metallic elements that are solid in state. For these types of chemical equations, writing this cell notation is out of the scope for these types of chemical reactions. The reason why is because you guys need more information in terms of how to build and set up those galvanic or voltaic cells. And so you guys do not have enough knowledge to be able to write the correct cell notation for chemical reactions that are mostly aqueous or gaseous or liquid in state. So long story short, I'm not going to hold you guys accountable to write cell notations for something like this, just because there's only one defined solid. The same can be said for this chemical reaction. So notice that here we have aqueous, 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 and we only have one solid, and then the rest is aqueous or liquid. And so I probably will not ask you to write a cell notation involving this type of chemical reaction, just because it's a little bit complex and it involves the addition of other metals and potentially hydrogen gas that's evolving. However, for these very simple chemical reactions, you guys should be able to write its cell notation or go from the cell notation and write the chemical reaction. So you guys should be able to go from this cell notation and write the chemical reaction. All right. And so let's go ahead and quickly solve this problem. Once again, we're going to use the standard cell potential to predict whether or not the forward reaction is spontaneous. And so for us to do so, we need to determine whether or not this value is representing the reduction, or this value is going to represent reduction, or this value is going to represent oxidation, or this value is going to represent oxidation in our calculation. And so to ensure that we're going to put those two numbers in the correct position in that equation to calculate the standard cell notation, we need to write out our oxidation numbers. And so for your oxidation numbers, just go ahead and ignore all your coefficients. Electrochemistry, it is intensive. Most of these calculations reflect intensive properties, and so therefore the amount is it's independent of the amount. And so for I minus, the charge is going to be -1. So for bromate, we know that this oxygen is going to be -2. However, this bromine, since it's in the position of what's normally observed as the cation, we actually need to determine the oxidation number for bromine. Hydrogen ion, that's going to be +1. Here we have this diatomic iodine that's in solid form, so we know that it's going to be 0. Since this bromine is by itself, its charge is going to reflect the oxidation number. Hydrogen is going to be +1. And oxygen that's not in a peroxide is going to be -2. So now that I've listed all my oxidation numbers, I'm going to go ahead and start comparing them. And so if I look at, for example, I minus and, take it back. So if I look at iodine and iodine before and after the chemical reaction, notice that there's a change in oxidation number. So something happened, okay? And so if I were to look at, for example, hydrogen, notice that it's +1, here it's +1. So nothing really happened with hydrogen, so I'm just going to go ahead and ignore that. And so notice that I still have an X value for bromine. I would ideally like to determine the oxidation number for bromine just to be certain if it's undergoing oxidation or reduction. And so for bromine and bromate, since we don't know the charge of bromine, we're going to set that as X. And since there's only one bromine and bromate, it's going to be 1x. And then I'm going to add that to 3 times the oxidation number. And the oxidation number for oxygen is -2. Now, in the previous example, I said that everything equals to 0. But here in this case, notice that there's an overall charge of -1. So therefore, the overall charge is not 0, it's -1 for bromate. And so solving for x, I get -6. This is going to be -1. X is then equal to +5. So now that I know the oxidation number for bromine and bromate, which is going to be +5, I can go ahead and compare my bromines. And if you look, my bromines have different oxidation numbers before and after the reaction. And so if I were to compare the oxidation numbers, it looks like this the numbers went down. And so therefore this is undergoing reduction. If I look at iodine, notice that my number went from -1 to 0, so it's going up. My oxidation numbers are going up, and therefore the process is going to reflect oxidation. Okay. So now that I know the substance that's oxidized and reduced, I can go ahead and assign that concept to my given reduction potential values. And so since bromate is undergoing reduction, let me do this in a different color. Since bromate is undergoing reduction, then this number here, this 1.44, let me write the equation first. And so since this bromine, or the bromine and bromate is undergoing reduction, then that means this 1.44 is going to go in the front, leaving me with iodine, which is undergoing oxidation. So therefore, this value, 0.54, is going to go behind the minus sign. So here I have 1.44 minus 0.54. And so that value in volts, so if I subtract those two, that's going to give me 0.90. And so since this value is positive, this is telling me that the forward reaction is going to be spontaneous. Now that will tell me implicitly that the reverse reaction, if I were to reverse this reaction, it would be non-spontaneous. And the calculated value for the cell potential would simply be negative 0.90. So you just flip the sign, but you keep the number. If I want to describe the reverse reaction. All right, so this is pretty much it for this section. We'll go ahead and talk about the relationship between free energy and spontaneity in the next lecture video.